Alrighty, so then we have these problems. Key authentication, shared key authentication is not working properly. Okay, so that is the trouble for WEP. So attacker can install plain text, as I said, and resulting ciphertext. This is this one, R and K encrypted R, basically, and then they can get the pseudo-random key stream produced by RC4. Okay, so your RC4 key is revealed. Okay, is revealed. That is the idea. Okay, and let's have a look at another flaws. First of all, WEP does not meet fundamental goals of wired equivalent confidentiality, because WEP stands for wired equivalent privacy. So in other words, we were looking for something that's equivalent to the wired environment security. Okay, but here in the environment we are using, let's say, AES algorithm, but this does not provide that level of confidentiality. So it fails to meet expected goals for integrity and authentication as well. And has two generic drawbacks. Okay, use of WEP is optional. No one is forcing you to use this one. Okay, and then many real installations never even turn on encryption. Okay, and by default WEP uses a single shared key. Okay, and common to all users of WLAN. Okay, common to all users of WLAN. Stored in, that's important, okay? Because every time, all right, let me put it this way. In security, every time we are focusing on how strong the algorithm that I'm going to use, okay? And we are measuring the security in different ways. And they said, for example, that AES is very, very secure algorithm. It's not easy to break. Okay, fine. And they are telling me that this is true, and I do accept that AES is good, and I decided to use the AES in my application. Fine. So I selected the strongest standard encryption algorithm. Okay, and this algorithm is using 128-bit key size. And I generated my key, okay, 128-bit. So where am I going to put that key? How am I going to store that key? I stored in my hard disk in a file saying that encryption key. What's going to happen? If there is a security compromise on my machine, people will be able to discover the key. And this way, it doesn't matter anymore whether I am using a strong encryption algorithm or less strong encryption algorithm. So in other words, the security is going to come not only from the algorithm itself, but the use of the algorithm is going to play a very important role. And one of the major things is the key management. How you're going to manage your keys, how you're going to distribute them securely, and how you're going to protect them securely. It's like password. They said that, okay, select very strong passwords. All right, you are selecting very strong passwords. That's going to be access point for almost every application that you are using. Okay, but when you select very strong password, it's not going to be easy to be remembered. We are not going to be able to remember it easily. What are you going to do? You're going to write them down. Okay, if it is a signal, one simple password for every application, that's another point, because you are creating some kind of choke point. If there is any security compromise on your password, every stuff that you are using that password is going to be opened. Okay, so what you're going to do? You're going to select strong password for each site that you have an account. Okay, but selecting secure password is not going to be easy. Okay, especially for each account. Good God, it is a big deal. How many passwords you guys are managing in your daily lives? So many, right? Right now, every website that you visit requires an account. Okay, how you are remembering all those passwords? I'm going to tell you. You don't select a different password for each site. Either you have one or two passwords, and you are using those one or two passwords for every site that you are visiting. And they are easy to remember, by the way. Okay? It's not going to be that hard to remember, because otherwise you have to write it down. You see, security becomes management of the passwords. If you are writing them down, even if you select a strong one, you have a security problem, because you wrote them down. You have to keep this document secure right now. There's another security challenge for you. If you lose this one, you lost everything. It's the same thing over there. You have a very strong algorithm, but hey, you are actually storing your keys on your hard disk, okay, open, not protected, then you're going to be in trouble. Strong algorithm doesn't mean anything anymore. Okay? So that's why while we are discussing this WEP, when we are discussing this KAV or RC4 key, then you have to ask me this question: where are we going to store those keys? Okay? And stored in software accessible storage on each device. So that means that any compromise in the device, forget the key. Okay, forget the key. But everyone is using the same key in one AP environment, right? So then this time you have to change the key for everybody. Okay, for everybody. But how are you going to distribute those new keys? We don't have any distribution mechanism. We don't have it in WEP. Compromised device means you have to change the keys on all devices, as you see. Okay. So then WEP, based on this discussion, WEP lacks a key management protocol. We don't have it. We don't have it. That is actually, in my opinion, one of the biggest security weakness in IEEE 802.11 protocols. Okay. So the distribution of new key becomes tedious and possibly long process, depending on the network size. Okay. And the other important thing is, for the WEP, you see, we keep telling the problems with WEP. All right. Encryption keys can be recovered through cryptanalysis. We are not going to go into the details of that one, but if you have enough pairs of this encrypted the messages, you may get keys, or you may identify the keys, because it is using stream cipher RC4 in a non-standard way. Okay, in a non-standard. What is the meaning of non-standard way over here? Remember, in stream ciphers, there is a rule. It says that the key that is used must be never used again. That is the major thing for the stream ciphers. If you are reusing the key, then you are in trouble. You are disclosing your key actually. Okay? You are disclosing your key. For one message, you're going to have one key. That's it. But if you are using the same key for the other message, I'm going to have two different versions of the encryption of the same message, so that I can break this algorithm. So that is the way non-standard, because RC4 eventually is going to repeat the keys that you are using. Okay? And it contains base key with 24-bit packet key. We call that nonce. Nonces are random numbers only. They are trying to use this one because it's a random number to make the key unique key. Okay, unique key. But again, 24 is limited basically. So that there is quite a limitation over there. So the result is going to be, as I said, per packet RC4 key. If you are using this one again, you're going to be in trouble. In August 2001, we called it FMS attack. Florder, Mountain, and Shamir shows eavesdroppers attack when they have several million encrypted packets whose first byte of plain text is known. First byte of plain. This is called known plain text attacks, by the way. Okay? They managed to break this algorithm, and they find the RC4 key. They find the RC4 key. Okay? Because they know the RC4 key schedule, I know. Okay? And after this one, there's another attack, SIR attack. This is, again, the names of these guys. Okay? And implements the attack, demonstrates that real systems can be cracked. Okay, first octet encrypted under WEP is again known, but this time is known fixed value. Yes, yeah. RC for what? RC for key schedule is the generation of the key in the RC4. In other words, how RC4 is working. Because it's shuffling a lot of bytes. So what is that shuffled stuff in RC4? Algorithm itself, in other words. Okay? So SIR says that if the first byte is known, they can break the algorithm, okay, in few hours of eavesdropping. In few hours. This is not a big deal. Again, if you are interested in those things, go and check it on the internet. You will see the details, how they are doing it. Okay, how they are doing it. And there are public tools implementing SIR. So if you want, you can implement yourself. Okay, because this thing is free. Okay, and that's called AirSnort. Okay, AirSnort. When you get that software, download it, install it, you can actually mount a SIR attack. Okay, SIR attack. So you can break this WEP yourself if you want. Yeah? And this is free. You don't have to pay anything. Yeah? You don't have to pay anything. Okay, what else? Let's have a look. Other known attacks. Walker. Small IV sizes creates risks of key stream reuse. As I said, it does not provide too many possibilities for the new keys. Okay, and then if that is the case, they can find the keys. This BGW attack showed that encrypted message can be modified. Showed that the user authentication trivially defeated. Okay. By the way, these guys are Berkeley guys right here. Okay. These were the students, and they just managed to break this algorithm like this. And this guy says that could decrypt at any chosen packet in few hours. In few hours. So in other words, that means that this WEP is already in trouble. That is the result of our discussion so far. Okay, with the confidentiality. Okay, because it doesn't provide a very good confidentiality. Okay, and integrity and authentication goals are not good enough. We are not getting integrity, we are not getting authentication, or we are getting very limited integrity, which is not suitable for cryptographic applications. Okay, well, we don't get authentication at all. Okay, at all. And then attacker can forge new encrypted packages which will be accepted by APs anyway. And attacker can join WLAN and or attack other hosts because authentication failure. All right. And how are we going to fix all these things? Okay. Right. We understand that the confidentiality is in problem, integrity is in problem, authentication is in problem. Okay. So how are we going to fix that stuff? So let's have a look at that one. One thing is called Wi-Fi Protected Access, WPA. WPA. What we are doing, introduced in 2002 by the Wi-Fi Alliance, okay, security standard for WEP, okay, and substitutes WEP to provide more security and interoperability services. That is important. Will be forward compatible with IEEE 802.11 I protocols. So this is going to be, this WPA, going to be part of IEEE 802.11 I protocol. Okay? So let's see what's going on with that one. IEEE 802.11 I does offer two solutions. First one, Temporal Key Integrity Protocol, TKIP, short-term solution, WPA. Short-term solution. Counter mode CBC MAC protocol, CCMP. That is the real thing for the long-term solution. Long-term solution. Well, right now when you got the modems, on your wireless modems, who are working in IEEE 802.11n protocol, that means that they have the I, security stuff, so they have these two things, TKIP and CCNP. CCNP. So in TKIP, we are not going to change RC4, but we're going to make the RC4 stronger. We're going to increase the key sizes, we're going to increase the randomness of the key, so on and so forth. And also we're going to replace the CRC with another algorithm called Michael. Michael, the name of the algorithm, hash algorithm that we're going to use is going to be Michael. Okay? But the encryption algorithm, I'm not going to say encryption algorithm, but the key that we are generating for the XOR encryption is going to be RC4 still over here. But right here, it's going to be AES. We are completely changing the encryption algorithm right now. Completely changing. There's no RC4 at all anymore. No RC4 at all anymore. And they go into the standard AES algorithm. AES algorithm, as I said, the key size of the AES algorithm is 128-bit, but it can be used for 256-bit key sizes as well. It comes with an option. So for a long term, that's gonna be secure, let's say within 10 years or something like that. 10 years, you can say that 256-bit key sizes are gonna be quite enough. And why they selected AES? And we said that the RC4 is selected over here because of the performance. Okay. Right now, when you implement AES, implementation of AES is actually quite fast. You are implementing just 4 tables. That's it. That is the implementation of AES. Just 4 tables. Each table is around 4K or something like that. It's a lookup table. You're going to go and look up some value over there. You're going to take that value. Okay? It is very simple. So in other words, performance of this one is no less than RC4. Okay? No less than RC4. So okay, let's have a look at the details. So let's try to understand these things much better. Final product that has these two is called IEEE 802.11i Robust Security Network, RSN. Okay? It's called RSN. So we have RSN right now. RSN. For access control, it's going to use IEEE 802.1 protocol for port-based access control. So they are going to close or open the ports to gain access. Okay? So we are not going to go into the details of that one, but these two things is going to be really important for us. Authentication and key generation. Authentication and key generation, they have a new authentication protocol. It's called EAP. It's called EAP. Extensible Authentication Protocol, and we will see, and I will explain how they are using these things. Okay? And for confidentiality, data origin authentication, integrity, and replay protection, they are going to use TKIP or CCNP. Okay, TKIP or CCNP. So let's have a look what's going on with those things. Confidentiality is going to be provided in TKIP by using RC4. So RC4 is going to generate the key again. Basic thing is WEP, but this is much more secure WEP. Okay. In CCM, they are using AES counter mode. AES counter mode. Do we have any idea about counter modes of any encryption algorithm? Counter mode? No? Okay, so what we are doing is, let's say that this is the encryption algorithm. Okay? If you remember, encryption algorithms are encrypting the messages block by block. Block by block. Okay? Block by block. So then there will be a plain text. Okay, plain text, and there will be a key. Okay, there will be a key. And this is going to be the ciphertext. Okay, this is going to be the ciphertext. So what we are doing over here is that this key is going to be XORed with some kind of counter value. Okay, it's a random number. It's going to be incremented. Okay, it's going to be incremented in the other stages of the encryption. So this can go like this. Okay, so this is called counter mode. Counter mode. Where are you? Yeah, AES counter modes. And if you go to the CBC mode, cipher blockchain that is, okay? In cipher blockchain, this ciphertext is going to be XORed with the next plaintext block. Next plaintext block. Okay, again, ciphertext of the current block is going to be XORed with the next plaintext block. So that's called CBC, cipher block chaining. Okay, cipher block chaining. And go and check those things from my presentations. Anyway, I already gave the detailed information about CBC and CTR. So check those things and make sure that you understand the stuff. Counter mode is quite fast. Okay, so it is used all the time for the fast applications. So that's why in the confidentiality, CCM is using AES in counter mode. And then they are also using NIST wrap, but the actual thing is the CCM AES counter mode. We are not going to go even the details of this NIST wrap. Okay, it's not a big deal for us right now. For integrity, oops, they are using HMAC SHA-1. Okay, HMAC SHA-1. Okay, to refresh your memories again, I have to tell something about this HMAC. HMAC is called hashMAC. Okay, we have two algorithms which produces digest of the message or a fingerprint of the message. Okay, digest of the message or fingerprint of the message. What I am saying is basically this. Let's say that I have a message and I have an algorithm, okay, and that creates a fixed length output, okay, no matter what message size that you have. Okay? So this output is not related to the size of the message. Let's say that your message is 1 gigabyte, but the output is 128 bits. Okay, 128 bits. This 128-bit output is going to be called ICV in our case. Okay, it's going to be unique to that message. You are not going to find any other 128 bits, okay, for different message. This is going to be unique for this message. And there are two ways to calculate this, okay. One is you may use a secret key and the algorithm, okay. In other words, algorithm requires a secret key, so then this output is called MAC output. This output is called MAC output if you have a secret key. If you don't have a secret key, if you are actually generating this fixed length output by using some algorithm, this output is this time called hash output. Hash output. The algorithm is called hash algorithm. Okay, hash algorithm. Most of the security applications in today's world is using SHA-1 hash algorithm. Okay, SHA-1 hash algorithm. That is a standard. Okay, that is a standard for most of the security algorithms. Okay, for most of the security applications. But that is going to change in the very near future. That's going to be SHA-512. That's going to be SHA-512. In SHA-512, this output, this fixed length, is going to be 512 bits. Okay, 512. That's the new standard. Okay, but SHA is hash function. So it does not require a secret key. But if I can make some modifications, if I can use this SHA-1 in a way that it requires a secret key, that's called HMAC. It is an algorithm actually. Go and check the details of HMAC. But what is important for us is that HMAC makes the SHA-1 secret key related. So this output in HMAC requires a secret key. So don't forget this one because this is going to be important for the key generation and distribution. So in other words, in TCP and CCM, okay, we need another key that is going to be used to create ICVs. Okay? But in the previous WEP, CRC didn't require any key, secret key, right, to generate ICVs. But right now, for that ICVs, we need another secret key. So you need a key for confidentiality, and you need a key for integrity. Okay? And you may use HMAC MD5, but TCP is using Michael we call it MIC algorithm, message integrity code. Okay? So the output is called message integrity code, micro algorithm. And CCM AES, the CCM is using AES CBC MAC. So they are actually using AES-based MAC algorithm in CBC mode. They are just taking the last output as an integrity check value in this scenario. Okay, So you see, they totally moved into standard and more strong algorithms. Okay, more strong algorithms. And for key generation, they are using HMAC SHA-1, okay, or RFC 1750. Okay, generally they are going to use this HMAC SHA-1. So we're going to have something, okay, and we as an input, and the output is going to be some keys. But don't forget, we're going to have confidentiality key, and we have to have HMAC key. Okay, so how we're going to generate those things is going to be very important. So that's going to be based on this key generation algorithms. Okay, that is for RSM. Are we clear so far, guys? Okay. So let's have a look how the phases of the operation is in this IEEE 802.11i. So first of all, station is going to try to discover the available or APs that is in your coverage, or that's in the SDA's coverage. Okay, and then in phase 2, as you see, there will be an authentication server. Okay, and then there will be an authentication. See, there will be an authentication. And then they are going to, after authentication successful, they are going to generate the keys, and they are going to exchange the keys, and they are going to distribute those keys. Remember, in WEP we didn't have that stuff. Okay, we didn't have that stuff. Then phase 4, protected data transfer, because you have the necessary keys right now. Okay, you can encrypt the data, you can calculate the mix, ICVs, whatever you wanna calculate. So when you finish everything, connection termination between STA and AP. Okay, are we clear with these things? So let's have a look at this key management and protected data part. So that's going to be important for us. So this discovery and authentication process. Station is going to ask AP, they're saying that probe request. AP is going to send possible security parameters, whatever those parameters, like security capabilities set per security policy. It will say that, hey, I have these algorithms, I do support these algorithms, I do support these protocols. Okay? And then probe response is going to come over there, and the station is going to send a request to perform null authentication. That is open system authentication request, if the system is open. Okay? Because you don't have to do the authentication every time if you try to gain access to the Starbucks network, right, in Starbucks. So that's why you have to have this option, open authentication option. Okay? So this is open system authentication, AP performs null authentication. If it is not open, then station sends a request to associate with AP with security parameters. It will say that, hey, I'm having these protocols, these algorithms, and this stuff. Okay? And then AP is going to send associated security parameters. Then the station says selected security parameters. So they are going to decide about the security parameters that they are going to use. Okay? Then the control port is going to be blocked. Remember, ports are going to be controlled by 802.1x protocol. Okay? And then, based on this X, now we're going to have EAP requests. What is this EAP request? Authentication is success. We have the security parameters that we're going to use. Now let's generate the keys. Okay. Now we are generating the keys over here. Okay, generating the keys. And as you see, extensible authentication protocol exchange keys generated. They are accepting the key material, and then again we are doing it in the controlled port block. So what we did is we authenticated ourselves first, then we generate the keys by using EAP protocol. That's the idea right now over here. Okay, let's have a look how they are actually controlling the access by using the 802.1x. This is the access point AP, okay? And there is uncontrolled port and there are controlled ports, okay? There is an authentication server. When we do the authentication successful, you see it is not forwarding the connection request to any other parts of the network. So first of all, you have to definitely go to the authentication servers. So ports are blocked right now. You cannot access to other parts of the, in other words, you cannot gain access to the wireless network. Okay? But once the authentication server or the authentication is successful, this time either this port or this port, whatever the direction that you are going, is going to be connected so that you can exchange the keys and everything, and you can have the access to the network basically. Okay? So that is the idea. They are actually, if you remember the firewalls, in firewalls we have DMZ zone. DMZ zone is demilitarized zone. It doesn't have any physical connection with the network. You put the web servers and everything over there. It's the same kind of stuff. Authentication server over there, it should be public, open, because I have to authenticate every access. Okay? Once the authentication is successful, then I'm gonna route this guy to the appropriate port so that it can access to the network. Either this is a distributed system or other wireless station inside the BSS, basic service set. Okay, are we clear with this one? So I'm going to open or close the port depending on authentication. That's the whole idea. Okay, that's the whole idea. Okay, so how are we going to manage the keys? Now this is the management of the keys. Okay, this is management of the keys. We have two types of management of the keys. I said that EAP is used mostly. Okay, fine. The other one is out-of-band paths. So in other words, hands-on you can also manage the keys. Okay, hands-on you can manage the keys. First one is pre-shared key. That's called pre-shared key. You're going to write it down. You're going to go to the machine or you're going to go to the AP. You're going to actually install the keys. That's why it's called out-of-bands. Okay, out-of-band. It is 256-bit user-defined. Okay, it is user-defined. Fine. But that is important for us, this one. Okay, EAP method. This is going to be authentication, authorization, and access. Okay, keys. It's going. You're going to generate more than 256-bit a random number. Okay, and they are going to generate 256-bit random number. Okay, and this random number is going to be truncated. Okay, and then 256-bit is going to be pairwise master key, following EAP authentication or PS key, and then we're going to go to a pseudo-random function using HMAC SHA-1. So this is going to be input, this 256-bit or more than that one is going to be input to HMAC SHA-1, and the output of this HMAC SHA-1 is going to have this, either 384-bit CCMP keys or 512-bit TCP keys, or we're going to have doing four handshakes. These are the handshakes. We're going to get key CK, EPOL key, confirmation key 128-bit, KA key, EPOL key, encryption key 128-bit, and temporal key, that's going to be the actual keys that we're going to use, 128-bit for CCMP and 256-bit for TKIP. Okay? So these are going to be the keys. So these keys are components of PTK. So in other words, this PTK will have these keys. Okay, will have these keys. This is the key generation. As you see, key generation is totally based on HMAC SHA-1. So they are going to generate these keys for HMAC. So let's have a look at the usage of these keys. Maybe you are not very clear about what we are doing over here. AAA key, authentication, accounting, and authorization key. Okay, used to drive PMK, used with IEEE 802.11x authentication and key management protocol, same as MMSK. More than 256-bit key size, Okay, key generation key, that is actually your root key. That is actually your root key. Everything starts from there. Everything starts from there. You're going to generate a random number more than 256 bits, okay? And we're going to generate the other keys based on this key. Okay, based on this key. Pre-shared key becomes PMK in the pre-shared key environments. 256, that's the root key for that part. PMK, pairwise master key, this is important for us because that's going to be affected by this one. Used with other inputs to derive the PTK, okay? That's key generation key. And then group master key used with other inputs to derive GTK. And PTK, pairwise transient key, derived from PMK, comprise the EPOL KCK and EPOL KEK for TK and for TKIP. That is the composite key for TKIP and CCMP. Okay. And we have temporal key, that's for traffic, and group temporal key for these guys. Okay. And MIC key, this is important for us, 64 bits. EPOL key confirmation used to provide integrity protection for key material distributed during 4 handshake. This EPOL is for this 4-way handshake. And key used to ensure the confidentiality of GTK. Now you are protecting the other keys as well. Okay? And other key material in 4-way handshake. And finally WEP key, where it was used with WEP. You see they are going to go and generate these pairwise keys. Okay, pairwise keys. And you can also generate group keys. It's going to be valid for just one group. There will be a group master key generated by the authentication server, okay, and changes periodically, or if it is compromised. And then we're going to have group temporal key. As you see, this line shows that group temporal key is going to be generated by using HMAC SHA-1. Okay, HMAC SHA-1. So HMAC SHA-1 output is going to have 40-bit or 404 bits WEP, 128 bits CCMP, and 256 TKIP. Okay? And changes based on the policies. So you can actually establish group keys, or you can actually establish pairwise keys. Pairwise keys. So this is the key management. This is the key management that we are having right now with 802.11i protocol. So you thought that WEP is complex. You see, things are getting more complicated. I'm sure that right now you are saying, hey, what did this guy said? I mean, what is this PTK? What is this PMK? What is this KAK? Don't worry about these things, okay, too much. Because I'm not expecting you guys to understand it immediately. You're going to digest that information while you are doing your research, while you are preparing your e-portfolios, and while you are studying this course, basically. That's not easy to remember these things like this in 1 minute, in 5 minutes, okay? Most probably you heard these guys just now in your life, okay? So give yourself time, you will get you will digest the information, okay? So don't worry about too much details right now, because we're going to see a lot of details later on for other things as well, okay? I'm going to say the same thing. Give yourself time, review the videos, study, go and check on internet. That is very important for us. You have to do the research, okay? You have to do the research, okay? And also, if you don't understand anything, post a question in discussion board. Okay? Maybe some other guys know something about it so that they can share it with us. All right then.